To have Heino Falke talking about one of the most fascinating science discoveries in recent times. Heino is currently professor of radio astronomy and astroparticle physics at the Radboud University in Nijmegen. He has obtained his PhD in 1994 in Bonn and subsequently spent several years at the Universities of Maryland, Arizona and again Bonn before landing at Nijmegen in 2003. Heino works in theoretical as well as in experimental radio astronomy. Already in 2003, he has predicted that it should be possible to make measurements near the edge of a black hole. That was proven right a couple of years later. However, the most spectacular breakthrough was what went through all media last April this year, namely the direct image of the shadow of the black hole at the center of the galaxy Messier 87. Heino served as the chair of the Science Council of the Event Horizon Telescope, which made this observation possible. Apart from that, he's also involved in other radio astronomy projects, such as the so-called low-frequency array and the square kilometer array. Heino has won a variety of prizes, awards, and grants for his work, for example, the Dutch Spinoza Prize. Now let's hear the story behind this wonderful discovery. Please go ahead.
Thank you very much for coming today in this misty and foggy, rainy day. I hope I can make you cheer up a little bit with some of our results. Of course, you know some of them, but I give you a bit more of the story and the background. I'm not allowed to show you any of the new results, as you know this game. But I hope there's some time to discuss and answer your question that you may have. Let me start, as always, with pointing out that sort of a lot of the momentum we received and funding in Europe from the European Research Council, there was a synergy grant that we got in 2004, together with my colleague Luciano Rezzolla and Michael Kramer, which gave us 14 million euros to actually participate in the Event Horizon Telescope, which was actually the largest and the first really big grant that got this new experiment running, with included then a number of European partners that were participating here. The Event Horizon Telescope Consortium was formed in 2017. Actually, we signed the documents only after we did our first experiment. Took us a couple of years to form the consortium, actually longer than to analyze the data almost. It consists of 13 stakeholder institutions in Europe, in red here, including our university for the Netherlands, in the US, Harvard, MIT, Arizona, Chicago, in Asia, Canada, and Mexico. So it's truly a global collaboration because we need the world to this experiment. This was our first and until now only face-to-face collaboration meeting after we signed the collaboration agreement in 2018 in Nijmegen, with about 120 of our colleagues coming to Nijmegen. Total collaboration was about 250, but in the final papers we had about 350 people who contributed in some way or the other to the results. See all kinds of smiling faces here because at that time we already knew the results, which we still had to discuss how to write them up. At that time we hadn't written this, we actually hadn't written a single paper until that moment. So we had to invent, as we went, how do we write papers, how do we organize ourselves, and so forth. So this was all, very, very fast in the end. Now, it was always like my dream to actually see black holes. This is, one of the things that really attracted me into physics and certainly astrophysics, because I always thought that, this is one of the big challenges, unsolved questions. How do we understand gravity? And how do we rhyme gravity with particle physics? And I always wanted to be near black holes because that's where, gravity is the strongest. This is where things are going to happen. If you want to see black holes, you have to go to the really big ones that are the largest on the sky. And there are two which allow this, which already have a long, long history. One of those is the galaxy M87 that you mentioned already. This is a galaxy 55 million light years away. This is in the center of the Virgo cluster. This is the closest big cluster in our neighborhood. You know, there are filaments in the universe, and this is a big cluster in our neighborhood. So, and that is the central galaxy in there, which was created out of mergers of many smaller galaxies over the lifetime of the universe. So it really is a special one. You know, this is the big one in our neighborhood. And typically, what we've learned over the last 20 decades, the bigger the galaxy, the bigger the black holes. Okay? So of the really, really big ones, this is the closest one that we have in the universe. This galaxy was discovered in the 19th century in France by Messier, who sort of made a catalog of all the nebulae, and this was sort of the number 87 in his catalog. It was actually discovered in the center of Paris. You know, in the 19th century, you would have observatories in the center of Paris. The Vatican Observatory was actually in the Vatican at this time, right? So it's impossible these days. You have to go to really remote mountains, but in these days it was possible. There was no street lighting. This elliptical galaxy, as I said, and actually in 1918, you see this little streak of light here. Heber Curtis discovered this little streak of light in there. And that was like 3 years after Einstein formulated general relativity, 2 years after the Schwarzschild metric was written down. Of course, nobody had any clue that this little streak of light had anything to do with the theory of gravity. But this was pointing right towards a very massive, supermassive black hole. This was one of the strongest radio sources discovered. It's also called Virgo A. Virgo because it's in the constellation of Virgo, and A because it's the brightest and the radio source there. What you see here, if you zoom in, that this light streak of light has also strong radio emission. We'll see later a zoom where we see more full the glory of this galaxy, which actually fills an entire bubble of gas shooting out with the speed of light from the very center. M87 was in the 90s. It was measured. The nucleus was measured and looking for the compact dark masses. In the 90s, people were looking at galaxies and they found the presence of compact dark objects. The stars were going very fast. You had to have a lot of compact concentrated mass. Of course, as you know, quasars were discovered at the end of the 60s, beginning of the 70s. Very bright galaxies at billions of light years from Earth. And one of the crazy theories at the time was that this could be black holes. Right? So this was, and still in the 90s, when I would go to conferences, we would have votes on, do we believe black holes exist, yes or no? Actually a third of the colleagues would say, I'm not so sure, probably not. And there were lots of arguments made that black holes cannot even exist, right? That they would not exist, still in the 90s. But what you would find here, what you'd see in M87, you would see actually an emission line gas in the very center with the Hubble Space Telescope, and then you would do spectroscopy. You'd look at an emission line, and you'd see it red and blue shifted. You would see that one side is red shifted, going away from you. The other one is blue shifted, coming towards you. That's just a Doppler effect. And from the velocity, you can just use Kepler's law and infer what is the mass in the very center. And that led to initially 2 billion solar masses and 3 billion solar masses revised in 2013. Now, I tell you that this is actually a mass which is still too small to be seen from Earth. Okay? And that's what we knew then. 10 years ago, there were other measurements made actually at the integrated, looking at the light from the stars. This disk is sort of like a disk which has some orientation and projection effects which you need to take into account. The stars go more or less on random cylindrical or random orbits, elliptical orbits around the center. And you can use absorption lines and measure velocity dispersions and velocities and how this develops. And from that, you can also derive a mass measurement, and that was giving you 6.5 billion solar masses in the central region of a few arcseconds. This is still, of course, many thousands of Schwarzschild radii, 10,000s, 100,000 Schwarzschild radii away from the black hole, but it was indicating there is a compact dark mass in the very center. The other region, of course, that has always been famous was the center of the Milky Way. In fact, when the quasars were discovered very quick in the 70s, Martin Rees and others pointed out, well, if there are supermassive black holes in these quasars, at a few billion years in the past, they should still be around today. So also our center of the Milky Way, our Milky Way should host a central supermassive black hole. That was a prediction, and should have similar radio properties as well, because how quasars were discovered was because of their unusual radio properties when radio astronomy became available. Now, if we zoom in to the center of the Milky Way, we don't see much because it's all covered by a central dust region out of which the stars form in the disk of the galaxy. So we have to switch over to the near-infrared, and that happened again also in the early 1990s when I did my PhD, and the first discovery was happening of the stars in the very center. What you see here is a movie over 16 years of one of the stars in the very center of the Milky Way, and you see how it goes on a elliptical orbit around something. Well, that something was actually this is the latest measurement from 2018. Last year it was published, and was actually the ESO gravity interferometer. This is actually when you combine the big VLT instruments, the 8-meter telescopes in Chile, 4 of those, into one big interferometer, which gives you higher resolution, and you get much better accuracy. And you would see then the star pass by that central point here, marked as black hole. In fact, you could see it every day move. You could literally make a movie how that star was going around that region. And from that, you get a perfect Keplerian orbit, an ellipse. From that, you can determine what mass is needed. And we have now a mass measurement of 4.1 plus minus 0.03 million solar masses in the very center, located in this one spot here. Now, there are other stars going around that point as well that you can measure. You have your speeds of more than 10,000 kilometers per second of these stars. Now, if you look in the radio, this is actually a radio image from an SKA square kilometer array Pathfinder experiment in South Africa, the Meerkat array. A recent image. I gave a talk 2 weeks ago at the Porchera Institute, and afterwards someone was saying, "Oh yeah, this was an artist's concept." No, this is actually a real image with radio telescopes, and the reason why it's so detailed and so much information is because it has so many dishes, so many telescopes combined into an array. I think 60 or something. So you get exquisite images out of this. It's really, really amazing. You see the plane of the galaxy. You see actually supernova explosions. You see here molecular clouds which are lighting up. You see magnetic field filaments. You see here Sagittarius A. That is the central region of the galaxy, which was actually discovered in the 50s already, which, by the way, allowed us to pinpoint where the center of the Milky Way was. Because in the 50s, the center, because of this obscuration of dust, we were 20 degrees off, finding where the center of the Milky Way is. And then the radio one would realize, okay, the center is there. It might still be misleading because that seems to be a supernova, a single supernova which went off 40,000 years ago, right? So it's really a temporal phenomenon. Though, of course, the integrated light would still peak here somewhere. But this region is actually very, very recent. If you zoom in, with the VLA, the Very Large Array in New Mexico, for example, you would see this spiral structure, which is actually inner edge of molecular clouds rotating with 200 kilometers per second around that region. So that was actually one of the first arguments to say there has to be a mass measurement in the very center. And if you zoom further in, you find a point-like radio source, and that was discovered in 1974 by Belek and Brown. Confirming the prediction that there should be, these compact radio sources, cores, in the very center, as we see it in quasars and other active galactic nuclei in the universe, which were suspected to harbor supermassive black holes. So, since then, this was suspected to mark the location of the supermassive black hole. And in fact, it turns out when you look at the stars, initially you would not see anything at the location, at the foci of these ellipses. But once you compared it with the radio, you would find that right there, around everything, where everything goes around, sits that radio source, and so all the mass seems to be concentrated more or less in this radio source, which has a size at the time when I was doing my PhD of it was already very compact. I think 30, 40 Schwarzschild radii. So it was already getting very close to the event horizon. Now, one thing to explain, which I hope is Because essentially, you have to start with your mind. You have to understand what you're seeing, right? So there are a lot of things in the universe, and you have to understand what you're looking at and where to look, what frequency and what techniques to use. And there's an endless possibility. You could wander through a forest and enjoy every little flower and tree and so forth. But which is the tree that's really important? And that requires theoretical understanding. What you see here is the spectrum of the center of the Milky Way, Sagittarius A star. Sagittarius A, again, A is the brightest radio source in Sagittarius, in the constellation of Sagittarius. And star because it was a very exciting source, okay? It used to be the compact radio source in the galactic center. At some point, people got tired of this. They said, it's really exciting. That's like nuclear physics and excited states, so add a star. That's why it became Sagittarius A star. That's the whole story behind it. So here we have 10 gigahertz, 100 gigahertz, terahertz emission here. And what you see is the radio flux from that source. You see it's slightly rising until the sub-millimeter wave regime, terahertz regime, and then actually cuts off. Okay, why is this? Well, we made some model. We essentially adopted models for quasars. First, the assumption is there's some gas inflow onto the black hole. And it turns out, if you go to the center of the Milky Way, it's not a quasar, obviously, right? So it's not a very bright emitting source. In fact, I called it a black hole on a starvation diet. That was sort of my title of my PhD thesis, Starved Holes in Active Nuclei. So it's very little material falling onto it. So it's very at the lowest level of accretion that you can imagine. It turns out that accretion then proceeds it's very tenuous gas. It's optically thin. You hardly see actually the accretion disk. Still a lot of discussions in the community. I'm saying you actually don't see it at all, and then some of my colleagues in Harvard say, "Oh yeah, we see it here in this case." But I believe you don't see it at all really. But anyway. Everybody agrees it's largely radiatively inefficient, so the gas falls onto it, it's optically thin, not too much radiation. And then you have in some of the model that we developed, which you see actually throughout the universe, that there are jets being produced. You see it in M87, there's actually material shot out, and we'll see that later. And so you start with you start with dense magnetized plasma, which then expands. Yeah? And so if you calculate, how this looks like, you start with the synchrotron spectrum here. This is synchrotron radiation, relativistic particles with a Lorentz factor of about 100. These are thermal energies of about 10 to the 11, thereabouts. And this is a non-thermal spectrum actually. You'd have optically depth here effects, which cuts off the spectrum here, and then you have here either sort of a quasi-thermal, optically thin part of the spectrum, like a black body. It's not really a black body, or actually a non-thermal power law, which extends higher. Now, then you shoot the jet or the plasma further out, then it expands. The magnetic field goes down, the density goes down, and so that peak shifts from here to here and here. In fact, you can calculate that back on the envelope, literally. And you find that the natural solution is really more or less a kind of flattish radio spectrum as this one here. And then one of the conclusion is that the low radio frequencies come from further out, and the blue and the high radio frequencies would come from further in. Okay, so the higher the frequency is, you're closer to you get to the event horizon, to the source of origin. And the conclusion we drew at the time was that the actually sub-millimeter emission would come from essentially within a few gravitational radii of the black hole, actually inside even the innermost stable circular orbit. Gravitational radius of a black hole is g times the gravitational constant g times m divided by c squared. That's the scale of a black hole. The event horizon of a non-rotating black hole is 2 gravitational radii, 2 gm over c squared, the Schwarzschild radius. Okay. And the innermost stable circular orbit is 3 Schwarzschild radii. And that emission was even inside that, it seemed. At least very close to it or inside. And then actually, if you go to higher frequencies, there's nothing at higher frequencies, simply because all of that disappears in the black hole. It isn't there anymore. So that was the simple picture, and that was a prediction it would come from near the event horizon. Now, we then quickly said, well, that's cool. If you have emission from that region, then you actually illuminate the black hole from all directions right near the event horizon, as close as it gets. how does it look like? How does it look like? And there were some calculations in the past already by Bardeen in '73, calculating how a black hole would look like in front of a star. Right? If you have a black hole passing in a binary star in front of the star, you would illuminate it from behind, and light would be absorbed. What we found is that for very different models, we're using very generic models. We don't want biased by our own perception of how it really looks like. Let's assume the gas is falling in, it's rotating, it's going out, whatever. How does a black hole look like? And it turns out, whatever you do, there would be a dark region of almost the same size. Right? There's almost the same size dark region. We call that the shadow of the black hole. Turns out this is more or less sort of the lensed image of the event horizon. That's the absence, the nothingness comes from photons disappearing in the event horizon. Then you have a ring around it, which sort of near the photon orbit. And we also pointed out at the time that this would come then, would have a size of about 50 microarc seconds in the center of the Milky Way and could be seen with sub-millimeter VLBI. So that was a paper in 2000 that we published, saying there's a shadow, and you could actually see this. This actually was from a talk actually I gave. I recently rediscovered this slide from 2000 and said, it actually said, whatever the models look like, the shadow is always visible. If there's a black hole, we are going to see it. Okay? That is a slightly different picture from what people were thinking of before. So this is the standard picture that people had. You have a disk, and you actually, if you go today like Hollywood, Interstellar, you'd still see the same kind of picture. You thin disk surrounding it. But then the hole that you see here actually comes from the hole in the accretion disk, because they would stop the accretion on at a certain point. But here we have actually the jet producing emission. It goes much deeper in. You illuminate it from all directions, and we'll see that this actually makes a much stronger case. This is actually still here at NASA. Interestingly, by the way, if you go back, we were the first ones to actually introduce this color scale, right? So as you know, this color is completely artificial, right? It's an artistic choice. Okay, and somehow that stuck, and so from Interstellar to now, NASA also changed after we adopted it then for the final publication, and now also NASA uses the same color scale to represent black holes. There's actually an entire PhD now written in I think in Oxford about sort of in the history of science and about the stylistic aspects of images in science, in particular black holes. So it's. Now, where does this all come from? Why is the reason why that we can see the shadow? Why is it such a clear, predictable thing? And that has to do with the photon orbit. In fact, that was already pointed out in 1916. I find this totally amazing. In 1915, you had Schwarzschild developing GR, and then you had Einstein GR, and then 1916 Schwarzschild developing the Schwarzschild metric, and then Hilbert, almost within a few months, for a lecture that he gave to his students, which later was published in a book. He calculated how light would be bent around the Schwarzschild metric. They didn't know anything about black holes at the time, right? That was the concept was even right? So event horizons. It was even people didn't like that. This is just it was a very weird concept at the time. But they would calculate what would happen. What you see here is you shine light on parallel rays. It will be bent, and there's a particular separation here, which is given by a square root of 27. M, or square root of 27 Rg, would be bent, and actually bent onto a circular orbit. So in infinity, it would actually be at a closed, it would never reach a black hole, would never go to the outside. Which means that any light ray that goes inside will actually go around or go half around and then end in the event horizon. So everything you see within this large region will end in the event horizon. Everything outside will escape. Okay? And so if you now surround a black hole with emission, now assume you have these yellow rays, for example, then let's start with the red ones. So the red ones are near the photon orbit. Okay, light comes in very close to each other, is bunched, but then it goes to the photon orbit, and then half of it goes in, the other half goes out. Yeah, it's a very sharp watershed. But if you turn it around and say, okay, I have emission from surrounding the black hole from all all of this is filled with emission, right? Then all of this emission will be bent towards the event horizon, will be bent into this ring, which is sort of around that photon orbit. So that photon orbit is the visual scale of a black hole. And also turns out, it's something that struck me when I, at some point, because people were saying, okay, yeah, but black hole rotates, and a small black hole has an event horizon of half a Schwarzschild radius, and a counter-rotating black hole has an event horizon of an innermost stable circular orbit of 9 rotation radii, for example. Yeah, so the hole in the accretion disk can be very small or very large, depending on the spin of the black hole. But for light, always goes left and right. Yeah, it goes sometimes with the spin and sometimes against the spin. And so these effects cancel so that the size of that shadow is almost always the same. So within 5%. Also, it's not exactly the same, but it's within 5% always. So that's why it's a clear prediction. Now, of course, today we do much more sophisticated simulations. We do general relativistic magnetohydrodynamic simulation. You essentially take the equations of fluid dynamics. You put in, you make ideal so a frozen magnetic field, no resistivity. So magnetic fields are dragged along, and then you start with a torus with magnetic fields, in a poloidal magnetic field configuration. You let it rotate. A differential rotation will make it accrete. Well, actually, it will accrete because of the magnetic fields. The magnetic fields will create some kind of a viscosity, and so matter will fall towards the black hole, and the rotation will actually curl up the magnetic field into like a spaghetti bowl here. If you let it evolve further, what you will see is in these simulations that, in fact, near the event horizon, near the inner edge of the accretion disk, we have sort of a you can't pile up all the magnetic fields anymore. They actually shoot up along the rotation axis of the accretion disk, and you can create those jets. And so this is the development of the last 10, 20 years. Now we actually can simulate black holes and jets very well in these big computer simulations. In fact, we can do these simulations in full GR, and also in non-standard spacetime. So, specifically for this project, we developed accretion codes that can do, any spacetime you give us, we can do an accretion jet, an accretion disk, and a jet, and we can do the ray tracing and the light bending in this alternative theory. So, actually, you can do it if we give you the code, right? So, I don't have enough people to do this. Now, this is actually a simulation that one of my students did. This is a VR-GR-RT 3D GR-MHD simulation. It's a virtual reality, general relativistic ray tracing, three-dimensional general relativistic magnetohydrodynamic simulation, so twice GR, sorry. But this adds sort of radiation, how light is bent, how synchrotron emissivity and absorption is included in full GR, in 3D, in virtual reality. We've chosen here parameterization to be more visually pleasing. All the effects are real, but sort of we've here amplified the accretion flow. We've also taken multiple radio frequencies. So you see all the disk, you see the jets shooting out, and so forth. Typically in the simulation, actually, jets can be much more prominent. Now, if you do the simulation for M87 with one frequency, this is what you see here at 3 millimeter. This was actually published in 2016. You see here the edges of this outflow actually are highlighted by the radiating electrons. This is where most of the hot matter is in this sheath of this jet. That's why it radiates so bright. It's not where most of the matter matters. It matters where the hottest matter is, right? That's what's happening. In fact, if you go to previous VLBI observation of M87, zooming in, you see that this sheath actually is prominent. Actually, in the last few years, we were able to explain this. And then you zoom in to a higher frequency. As predicted, you go to higher frequencies. So, what I initially said was back on the envelope. Now we do really full radiative transfer. You actually zoom in onto the black hole, and what's left is the prediction that we published in 2016 for M87, specifically for M87, how it should look like. So that was done before. I point this out because in astrophysics, typically, we always do post-predictions, and it's very difficult to get it right. And so this was actually done and published before the observations were taken. Now, of course, in order to see this, as I said, you need a resolution of, in the most optimal case for M87, 40 microarc seconds on the sky, and for the galactic center, 50 microarc seconds, slightly larger. And that is, as I always like to say, a mustard seed in New York as seen from here. And if you have 1 millimeter wavelengths, the resolution of a telescope is lambda divided by the size of the telescope. Lambda is 1 millimeter. So how big does D have to be, the size of the telescope, in order to give you 50 microarc seconds? Well, you need a telescope the size of the Earth, right? So that's a simple calculation. And so we built one. So, of course, you don't start from immediately. And actually, this technology is actually 40 years old. There was already a Nobel Prize for interferometry in the 70s when this was invented, right? And it's used in many applications these days, in MRTs and in tomography and so forth. But at high frequencies, it was developing again in the 90s, and now was sort of on a prediction level. The first, experiment detecting the galactic center was done in Europe, actually, with the IRAM telescopes in Spain and France in 1998, led by the Max Planck Institute in Bonn. And then in the 2000s, essentially after it was clear that the shadow became very interesting, there was a very strong push, in particular in the US, where you had California, Arizona, and Hawaii, and the experiments by Dolman et al., which had more robustness. They got it right. At the time, they were calculating the size and so forth of the galactic center. It was still it was 7 sigma detection. The people were, but it was essentially within the same measurements that were confirmed later. And then in 2017, we built this big experiment, now with more dishes. You had here again Spain, Arizona. CARMA was shut down in California. But Mexico was joining. In Chile, we had the big ALMA telescope. As you know, ESO and NRAO and NIOJ have together built this €1 billion facility in the Atacama Desert. And then here, the South Pole telescope, which was actually built for cosmology, but was then by the folks in Arizona, was equipped with receivers to do interferometry. The data will then be recorded at all these telescopes on hard disks. And then we do an interferometry experiment. We can actually digitize photons, okay? The reason is because we have so many photons, they actually, the phase space is completely flooded, with identical photons, so they become classical waves, right? So we don't have individual, we're not photon limited, we have classical waves. You can digitize them, we can store them on hard drives, so later in the computer, we can bring them together and do the interferometry, not in the lab, we do it in the computer. Okay, and it's phase. We record the phase as well as the amplitude of those photons. In fact, we digitize the photons with 2 bits. Okay, because we have sort of gigahertz sampling essentially, right, with 2 bits, and so statistically you sample them. You don't sample each individual peak in the electromagnetic wave. We were sampling 4 petabytes of raw data at all these telescopes. They were then later brought to the 2 correlation centers. Actually, everything we tried to do, we did twice with independent groups, geographically independent groups, different methods, different correlators, for example, here in Bonn and at MIT HISTEC. And the amazing thing that happened here was in 2017 that all the equipment worked, which usually is not the case. Sometimes telescope breaks down, or some equipment fails, and you go to remote locations, and always things go wrong. And the weather was fantastic for the entire period of observations. That also never happened in the 10 years before when people did their Pathfinder experiments. That all around the world you had great weather. 1 millimeter waves will be absorbed by water vapor in the atmosphere. So if you have clouds, if you have a wet atmosphere, then the waves will get stuck. That's why in the airport, right, you have to, when you're screened by millimeter or sub-millimeter waves, right, because it penetrates your clothes, but not through your entire body. This is equipment we installed at the telescopes. It's not shaking because of an earthquake. It's just because of me being oxygen deprived. These are just stacks of hard drive. Each of these things, boxes, has 8 hard drives with 6 or 8 terabytes in it. And so we were recording 32 gigabits per second data at the telescopes. People always ask, why don't you send it over the internet? Well, 32 gigabits per second from the South Pole is not a good idea, where you actually have only 1 megabit per second for 1 hour a day or so, something like that. Half a petabyte per telescope. We have atomic clocks, which have Allen deviation of 10 to the minus 14. Then we have ADC converters and down converters, which convert from the telescope frequency system to our digital system, which is like 0 to 2 gigahertz bandwidths. That's it. That's sort of simple. But of course, you have to make sure everything is right. You have to phase connect the entire system, and that's a lot of work afterwards. The actual observing run you see here on the live display that we actually developed here in Nijmegen. You see here we're observing actually M87 as the Earth rotates underneath, and then the quasar 3C279, one of the first quasars ever found, still use it, and 273. These are the 2 famous quasars, right, which actually started the whole thing. And we switch back and forth because we use the quasars for calibration purposes. In fact, we have to calibrate the gains and the amplitudes of the telescopes, and we did this first on the calibration sources before we went to the actual target source. We didn't want to use, spoil our, target as a calibration source. And you see that we sort of here strive to have triangles. Triangles are much more robust in terms of calibration of this. And then you observe 8 hours. In the end, you're left with about 2 hours actual observing integration time per day on this one source. So the image we show is from 2 hours observing. These are the telescopes here in Mexico, Hawaii, Arizona, Spain. I went to Spain here. It had the best food, I always say. It's actually true. Before I was in Mexico, there you only had to bring your own food. So it's deep fried pizzas, deep frozen, whatever. But you see, these are really mixed international teams. So we had one of our group members. So from each telescope had one of our group members, but there were also people from Harvard and other places, or from Mexico. So it was a nice, really international collaboration in all respects. So these were our friends in Chile. There's the Chiraco here and Helge. This was before the observations. This was after the observations, which were very tiring, as you can tell. It really was tiring, I must say, because we're working day and night, literally. What we actually measure in radio interferometry are the Fourier components of the image. Okay, every baseline in every direction gives you a measurement of a Fourier component of the image. And what you see here is a one-dimensional projection of the measurement of the correlation strengths that we measure, and that is related to the amplitude of the Fourier component of that image. And what you see here is what we measure, the correlation strengths. This is the real data, more or less. It's half of the data because this is amplitude only. We also measure phase. And you see that it drops to a null and then goes up again. And what you see here is the Fourier transform of a ring. Okay, you take a ring, do a Fourier transform, and plot it one-dimensionally, you get a null. And then from the location of the nulls, you actually determine the size of the ring. It's actually that simple. So you don't need to do any imaging, any tricks. You just measure this, you put that data through, and then you get it. The first is that looks pretty much like a ring. That's what we saw in May 2018. My heart was going boom, boom, boom when we saw that. This was actually too good to be true. But then you have more information. You have phase information as well, as I said. That actually is a true imaging aspect. And so this is how this works here. You have here, as I said, one baseline is like a single slit, a double slit experiment. You get a fringe pattern from this if you have a point source. Yeah? If you have a point source, a plane parallel wave, you get a perfect correlation. Now, if the source is a bit more extended, you actually the waves become decoherent. Like if you get very independent waves at both telescopes, because radio waves come from all over the sky, then you don't have any coherence whatsoever. Okay, so the strength of the coherence pattern tells you how compact the source is. And now you actually add more baselines. The Earth rotates, and then slowly the image, appears when you add more information, and you find it looks like a teapot. Okay, so I always say, so we show that actually Russell's teapot can be seen after all. So for those who know what Russell's teapot means, yeah, so we build up. So you see, it's not perfect. In fact, you can improve this by doing image reprocessing algorithms, because you don't fully sample the Fourier plane, right? So you can put some regularization constraint and so forth to actually make this better. Now, we did this, and I'll explain how we did this, but I now show you sort of the final result. Now, you've seen it, but I want to, I want to share with you sort of that zoom that we made when we released that image. So we now show this zoom from the center of the Milky Way to the very center of M87 with actual images, right? So all of this, except here, this is an animation in the beginning, but the rest are all actual images of M87. It's the biggest zoom in astronomy, a factor of 1 billion. So this is Virgo here, and we're zooming towards M87. Music, by the way, from my son. If you don't like it, don't tell me. You zoom in, you see a LOFAR image. That's where I worked previously. You see sort of this bubble of gas surrounding it. It's all coming actually from the central region of the black hole. And you see the VLT images, the optical, you see the jet here. You're switching to the radio again. You see this streak of radio light coming from the very center. Higher and higher frequencies, and then go to 230 gigahertz. And then that's the final result. And you clearly see, it looked like jet all the time, and then you go to 230 gigahertz and suddenly the thing appears, right? So, and we're using more or less the same techniques we used before. I think we did a much better job at calibrating these things and so forth than previously, because never before had one image been worked on by so many people at the same time, checked with so many different algorithms and so forth. I think that's probably the best checked VLBI image ever. Previously, people would be 2 or 3 people, sitting there and doing the data reduction. Now we had really 100 people, 50 people doing the imaging alone. And that, as you know, made a lot of waves worldwide. So this is really a lot of, and we were really stunned by. We were hoping that gets a little bit close to the attention of gravitational waves. That would have been, for us, amazing. But really, that was really stunning. Reaction on social media was also very positive. I think cats and black holes do really well. I mean, it's. In fact, my son plays football, and I was always at the football field. And then, after that, suddenly, people actually knew my name. So why? Because this was trending on 9gag. All the really bad jokes are shown, right? So this was. So the black hole was, yeah. Anyway, so how did we arrive at this image? Because I said there are some steps in between. I said calibration was an important step. We did this first on the calibrator sources. Then we had the first step was manual imaging, as we used to do in the past. So we had 4 independent teams which were not allowed to talk to each other and would make their own best image. In fact, each of them made multiple images. And when the data was released, everybody was rushing to their computers and making the image. So there was not a single place, not a single person who made the very first image. And it was not a single algorithm that actually made this possible. We actually used very different algorithms. Most of them, actually all of them, were already existing for quite some time, slightly improved. And so, these were the first images with not fully calibrated data. There was still some bugs that we knew of, which had to be improved. But all of them showed, again, the ring structure. And that now used the full information, not just the amplitude of the correlation, but also the phase information. In fact, also the closure phase and closure amplitude information, which is sort of more detail. And so that was, of course, the really exciting moment. And when I saw that for the first time, in fact, I was in that team here. I was like hovering about the ground for about 1 hour, and then I was really, frightened, because I knew now we have to really prove this is right. And I think that it was a gruesome period thereafter. Now, what we then did, we started essentially from scratch. Oops. We actually started with simulated data that would match the basic properties of the observations. We even added some extended structure of the jet and so forth. in the simulated data. But all of these would give you more or less would give you that pattern in the 1D Fourier transform that I showed you. These are rings, but they also filled disks. Give you something which is similar to a ring, not exactly. Or a double source. In one direction, a double source is like a ring. Okay. Or this is a full GRMHD simulation. And then we ran 3 different imaging algorithms over these, and we asked what is the best parameter set for each algorithm that reproduces all these images, all these simulated images, so that you don't want to bias towards just rings. If you know it's a ring, you can actually make better images to use regularizers who are optimized for rings, but you don't want to use this for a discovery experiment. So all of them were trained on very different algorithms. And then you would run a scripted mechanism to do this. And you see here 3 different algorithms. This is really a traditional VLBI experiment called CLEAN, VLBI algorithms called CLEAN. And these are maximum entropy methods, so you maximize the entropy in the image and have some regularization constraints. And you see all of them give clear rings with exactly more or less the same size within, I think, 1 or 2 microarcseconds. You see there are some subtle differences. So here you see a bright blob, here you don't. Okay? And that is purely an effect of the distribution of telescopes and the algorithm you use. So there is some ambiguity where exactly, whether the emission is 20% brighter or not. This is just not constrained by the data. So all of them are brighter in the south, but there's some subtle differences in where exactly how this is distributed. And that's just a purely systematic effect which you quantify. That's why when we published this, I later saw people who would then do their image processing algorithm on the final result and would point out, there are little edges in this, and I've zoomed in, I've sharpened it. It's just completely it's completely useless, nonsense to do. So anyway, so that's how good it gets. We then actually, many discussions on how to combine these things. In the end, we just averaged everything, okay? So it's not the smartest way to do things. We can do better, but that's what we did for the final image. And so here you see the average of the 3 different methods for 4 different days, because we had 4 different observations. And again, more or less the same structure. We see some slight deviation between the first and the last 2. We know there is some changes. In fact, it turns, in 87, it takes 3 weeks to go around the black hole. Okay, so within 1 week, there should be some changes, and we see some. Within 1 day, there should not be too much. But we can't really put our finger to it. And then the other step we did was to actually do, of course, simulations. This is also, I think, something that we added. And I think something we also, from the Black Hole Camp team, from the ERC team, we really pushed into this project. We really need good simulations to do this. And this here is, one of the simulations that we made. We actually made a big simulation library with GRMHD simulations for a certain parameter. We varied the spin, the inclination, the mass of the black hole, the accretion rate, the rotation of the rotating on the sky, and sort of the electron heating parameter. You see this nice photon ring here. You see the dark region in the center. You see stuff going around. And then we did this for a range of parameters. This is the largest GRMHD library ever made. But that gave us 60,000 snapshot templates, more or less, that we could then compare also statistically with the data. Which of these models is right. Well, I mean, the clear signature, all of them have a shadow, all of them have more or less the same size. So if you measure the shadow, it's directly related to the mass. This is something you can robustly measure once you have this. I mean, it's always, irrespective of the model. This is just what we said, in 2000, it's just now here with a massive parameter surge, essentially, more or less confirmed. But in detail, it looks different. So what we did here is 3 different simulations which fitted the observation best, or well, let's say. This here is one where actually the disk is counter-rotating to the black hole. Here's a non-rotating black hole, and here is one where it's rotating with the black hole. If you look at it, they all have the same, more or less the same ring size. We then also added, this is something also that didn't really exist to that quality before, full detector simulation of VLBI, with all the effects included. How would it really look like in the end? You fold it through the detector simulation, and you get this, and again, looks almost identical, which is good. It means, we really what we see is really matches the naive expectation, naive quote-unquote expectation of the model. But we cannot distinguish between spinning and non-spinning black holes. well, which was part of the prediction. Of course, at some point you want to go a bit further, right? And you want to find that. Let me see how much time I have. I think I'm a bit running out of time, so I may skip over this. There's a paper by Gralla, actually, who recently published some analytic ones, and he was claiming, he was putting out some counter simulations, counter models, very artificial intensity distributions. But it turns out, if you look at this was his strongest counter example. He would say, you see something inside. Yes, you do see something inside. The shadow is not dark. People sometimes call it silhouette. It's not a silhouette. We purposely call it a shadow because it's not a dark feature. There's emission before, there's projection and everything, right? So, but if the photon ring actually dominates, and if you blur it, you actually always get, even the counter example that he gave, within 20%, the error bars that we give comes to the same result as we do. So I think as I said, whatever you do, you always get this kind of structure. Unless you have the emission stop at, far outside, right? You create a hole that's larger. That's the only loophole you have. Now you can do a few tricks with this black hole. First of all, you can look at the width as a sec. This is 42 plus minus 3 microarc seconds. We have 3 different methods to test it, 3 different groups, 2 different softwares. If you take the distance to the black hole, take the angular width, then the mass comes out to be 6.5 plus minus 0.7 billion solar masses, which fits perfectly the predictions from the dynamics. And we were completely, we would have taken anything. So within the error bars is totally consistent. These are the 3 different methods. These are the error bars from the prediction from this the stellar mass measurements, and that's highly consistent. The other one is the circularity of this ring. It turns out to be remarkably circular, within 10%. And you can use this to actually place limits on the deviation from the No-Hair theorem. It's not extremely strong. So this delta Q over Q, this is the quadrupole moment, the non-Kerr quadrupole moment, and that's smaller than 4. It's a very conservative limit, I must say. But for neutron stars, for example, this parameter is already 10. So it's already, very, in that sense, a very, very good limit and the first one. And of course, you can do this better in the future, certainly when we get to the galactic center. Now, what do we do in the future? We want to have more telescopes. This is one of the projects I'm working on. Actually, I was just down at CMS. This is a 15-meter dish. So actually the size of your detector, more or less, right, in CMS. We want to put this on. This actually exists. We get it for free, but it's unfortunately in Chile, where we are many telescopes already. So we want to ship it to the Gamsberg here in Namibia to actually really get a much better coverage, particularly for the center of the Milky Way. I didn't talk about the center of the Milky Way. We're working on it right now. Wait for next year to see more results. But clearly, what we want is more telescopes, get better UV coverage, and then we can get sharper and better images. This is about a 15 million euro project where some money is already raised. Still trying to find more for this. We also couple this to an outreach program, in fact, where we are busy with right now in Namibia. We actually, in the Netherlands, we have this mobile planetarium where we go to all the schools and give a tour of the universe. And this was a test experiment, so to speak. We went to really the outer edges of Namibia, so really rural areas with a planetarium to just, see what the reaction was. And it was just phenomenal. I mean, there were 1,500, within less than a week, we had 1,500 school kids come to the planetarium. And one of my colleagues who sort of went to all of them, he said, when I arrived, there was a little boy coming to me, he said, "Are you a scientist? I want to be a scientist too." So, and for them, also interesting, like for the Dutch the school kids, they don't see the sky, so the night sky is very interesting. Right? For them, actually, it was interesting to see the Earth from the distance and see all the water on the Earth. So it's really quite nice to see. And actually, this is a local foundation which actually goes to schools anyway, and with which we are working together. And they have a mobile planet lab for desert research and climate change, and so they also want to do now astronomy, which I think is very nice. Now, what is the rest of the future? I mean, of course, the next step will be movies. We have individual images. These are here, black hole images with non-spinning, spinning, and so forth. And there are differences, certainly in the if you look this model versus this model, clearly the temporal evolution is very different from this one. At certain moments, they can look very much the same, but on average, over many, many epochs, they will look distinctly different. Okay, so we want to have more epochs to distinguish, hopefully also spin and other parameters better, and make actual movies. But that will require us to make observations essentially for M87 every other week. And for the galactic center, where actually the rotation timescale is 20 minutes, not 3 weeks, it's 20 minutes, because the factor 1,000 is smaller, we have to have more telescopes to sort of make better snapshot images. In the near future, I was just yesterday in Madrid, ESA Voyage 2050, we were proposing the Event Horizon Imager, 3 telescopes at 15,000 kilometers from the Earth's center, at slightly different orbits. 4-meter dishes, so it's like central region of CMS, and they would drift apart, and then the baseline connecting them will rotate and will extend and shrink, and then you get, this is the Fourier plane that you will sample. You completely sample the Fourier plane with this configuration. You have no atmosphere, which is one of the biggest adversaries at this moment. You can go to higher frequencies, which gives you also, you have longer baselines and higher frequencies, which gives you higher resolution. And so that allows you to make better images. This is for the galactic center. What I didn't say, there is a scattering in the galactic center, which also blurs the image at 230 gigahertz. If you go to 690 gigahertz, the blurring is completely gone. You see a really sharp structures here, and if you average it over time, you see a lot of stuff at 230 gigahertz, what we have now, but at 690, you're really completely dominated by the photon ring, right? You really isolate that clear feature of the metric, and then we simulate that, including the variability and everything, and so this is what you can recover from space, really razor sharp image. So nothing, this blurry thing. People said, it's a bit disappointing, this image, right? It's a very blurry thingy. True, it's still, I still love it very much. But, this is, and that's technology you more or less already have in-house, right? So we just have to wait until, it's your turn. But it's not that this is technology that is out of the world. I mean, this is technology that we could do. Well, how does it help us? What we've done here is actually a machine learning approach. So you take images, and then you blur them. It's 5 microsecond, 10, and 20. This is what we have right now, okay? And then we make a range of images, like the snapshots, and then we train a neural network and say, I give you that image, tell me what is the spin, what are the parameters of this black hole. And what you can see here is that, for example, the mass you can very easily reconstruct. The viewing angle mass accretion rate if you have this high resolution. Right? So you can actually, viewing angle within a few degrees, the mass accretion rate, the mass itself, to very exquisite precision. And this shows you the effect of the beam. This is the spin recovery accuracy. So 0.2 is completely random. This 20 microsecond, which we have right now. So it's completely random right now. But once you go to 5 or less than 5 microseconds to space, we get to a, perfect, not perfect, but, very high spin recovery accuracy from a single image. Of course, with movies, you can do even better. So I think there's a lot of promise to do that. You can also do non-standard GR. As I said, we're not doing it for you. Well, we did it at least in 1 or 2 cases. This here is a simulation of a boson star. So actually doesn't even have an event horizon. So it's just, you invent a very, very low energy boson, actually with a wavelength the size of the event horizon. So, I mean, it's really crazy. But some people claim this might be possible. And then you get something close to the Kerr metric, but you still get subtle differences, okay, in the appearance. And these kind of things and models you can test and see whether you can separate theories of gravity with each other. I want to end. I think I had 1 hour, right? So I want to end with a last comment on gravitational waves versus EHT, because we are now in a special, really, era. I think the first time that really approaching black holes on scales of the event horizon with very quantitatively measurements, and they actually probe very complementary different aspects. First of all, the mass, which is most important. In gravitational waves, you have stellar mass black holes of tens of solar masses. We have black holes of million and a billion solar masses. These are 8 orders of magnitude higher mass ranges. And one of the basic predictions of GR is that it's scale invariant. The size scale scales linearly with mass. That size of the black hole scales linearly with mass. And this we can now probe with over 8 orders of magnitude, more or less, and also with the same techniques. Once we have the galactic center, over 1,000, a factor of 1,000. So even and that is a very strong constraint on any theory. It has to be scale invariant. Of course, in gravitational waves, you have many sources. Right now, we only have 2 sources, but we can do many repeated measurements. We can do this over and over again. In gravitational waves, the source is gone, and then you cannot test what you have done. Right here, we can do it with improved technology, with space. This is really a predictive experiment. You can, you have more parameters right now from the waveform. That will not be true anymore once we go to space, and we get a lot of information. There are lots of pixels, that we have. Right now, we only have a few pixels, but they are very telling. The dark feature is actually very unique. But having a stable source also gives you multi-wavelength observations. We get an external mass. We don't have to derive the mass from the same. We have 2 measurements to derive the mass, which is a very important cross-check. In gravitational waves, you have to infer the mass from a theory that you apply to the data. Right? We have an independent measurement. And finally, we're actually probing the same scales. The gravitational waves are generated actually typically around the photon orbit, the same scale that we are seeing. Right? And the event horizon signature is this ring down, but it's still, you still have the same arguments about this. And here we actually see, essentially the light disappearing in the very center. And so what we can say right now from our measurements is, I think we have good argument that we see in the black hole shadow. And that the object actually has to be smaller than the photon orbit. Now, will we ever get to the event horizon? Of course not, because as you go to the event horizon, the closer you get, the redshift will get higher, and so once you go inside the photon orbit, you very quickly disappear in this sort of fog of this twilight zone where all information disappears to the outside world. Right? It becomes increasingly harder to get closer and closer. So maybe you get with an effect of 2 or a little more to the event horizon. But getting to an epsilon of the event horizon is almost impossible for any technique. Okay, sorry for the quantum gravity people, unless you have a prediction which is sort of on scales of fractions of the Schwarzschild radius. But size, shape, and structure fit GR. The mass is consistent. The shadow, what we see is actually signature of light bending in the Kerr metric. We measure the metric. We don't need the field theory of GR, so we have one assumption less to make. And really the absorption by the event horizon. So in that sense, yes, we do see the event horizon indirectly, right, by the absence of light. What's next? M87 polarization will be the next thing we'll publish. And then, of course, we'll be working on the center images of the galactic center. We'll have more observations in 2020. We'll have actually more telescopes, certainly for M87. Greenland and France will join. I hope that we get the Africa telescope going. That helps us for the Milky Way, which actually is scientifically even more important, I think. Eventually to space. Maybe we find pulsars in the center of the Milky Way. We can actually probe the space-time independently with a square kilometer array. That could be possible. And yes, we need to understand how we talk to each other between gravitational waves and EHT people. And the good thing is, that both sources and more will stay around for many, actually generations of PhD students to test and confirm what we've been doing. Thank you.
Thank you very much. There must be many questions.
Of course, you hope at some point.
Alvaro first.
You showed simulation that produced the jet.
Yes.
Are the simulated jets as relativistic as the observed ones?
That's a very good point. We simulate the innermost regions, and we see from observation that in the innermost regions, the The gamma factors are of order a few, not tens or so. But we know that the innermost region actually has a faster jet spine. And so it will be interesting to see whether we get to a Lorentz factor of tens or 20, which we see in VLBI, as the jet develops. There's good reason to believe so, but then that requires us to do much larger scale simulations. We're working on this right now. But for now, this actually seems to work out fine. For the region that we probe, it's sort of we get to moderately high Lorentz factors, yes.
Other questions? Urs.
You mentioned several times this linear relation between Schwarzschild radius and mass.
Yes.
And you gave a mass for the Virgo
yes.
M87. You said also that with this terahertz frequency that is irradiated from the closest approach, you are a bit away from the Schwarzschild radius. If I remember well, it's a force factor 3.5.
Yeah.
So with which precision can you, and with which model dependency can you state at this moment that what you measure as a size is the expected size of a system with a given Schwarzschild radius?
And that's exactly why we did all these simulations, where we actually changed the astrophysics. We changed all these other parameters. Changing the astrophysics means actually changing the location where the emission is made. So that one parameter I glossed over actually makes the jet brighter or the disk brighter. And it turns out that we are within 10, I don't know the exact, 10 to 20%, it always comes out to be the same. So that's a systematic error that we give. I think it's 10%, is sort of that we derive from those simulations.
So what you say is, given some model uncertainties in this model
yes.
that you fold in, within 20% you have tested the relation between Schwarzschild radius
yes.
and mass for that object.
And you get me because maybe that is even better than 20% at this point, but I have to look up whether it was 10 or 20. But yes. Yeah.
Okay. Questions?
That was the whole point about this simulation library. That was exactly. And as I said, it's fairly independent of where you put, because of this projection effect, right? Everything is projected towards the photon orbit. It doesn't even have to go around, right? But everything is sort of focused there, within a large range of the emitting region.
So in terms of timeline, when exactly next year should we expect to hear more about the Sagittarius A*? Is it going to be summer or end of the year?
It will be May 25, 3 o'clock in the morning. No, I don't know. To be honest, we had a very rough ride to getting the things published. We set the date when we wanted to be published things, and that was a nerve-wracking experience. And everybody said, we're not going to do this again. We'll publish when we're ready. We're not going to set any deadline. But I'm hopeful that somewhere next year, it definitely, I don't think it will be very soon. We want to take a bit more relaxed time now, to get things out. But we're working hard on it. So I think there's a good chance next year we'll have some results. Certainly, M87 polarization I think will come out earlier, and then Sagittarius A*, and then we'll see what we see. It depends on how good we can do the job, right? So it will definitely be more difficult than M87. That's clear.
And the second question is, when the Africa telescope gets installed, what kind of improvements or what level of improvement should we expect?
It's mainly for the, there are multiple improvements. One is, of course, the variability. The dynamic imaging actually is significantly improved. Also the robustness, something not to be underestimated, because right now if just one telescope falls away, and that happened in 2018. We had the Mexico telescope. Actually, it was an armed attack on, an incident, let's put that, on when our observers were going up to the mountain. And we stopped the observations. And there's just some difficulty situation in Mexico, in that region. We can't do anything about it. So if that falls away, it's almost impossible to make images for the galactic center. We are undersampled. If ALMA falls away, so having one more actually improves the robustness towards weather and as well. You can just have bad weather. Yeah, I can't tell you right now we're going to measure the spin or the ring width to that percentage. That number I can't give you right now.
Are there further questions or comments here?
So at some point you showed 4 images from 4 teams.
Yes.
And then you showed something that was simulated and reconstructed.
Yes.
So it happened in that order. First you looked
Yes.
at the actual data?
No. We first did the blind imaging manually, essentially. We then hard-coded the 3 different methods into scripts, tested them on simulated data. This was this array of simulated data. So all the simulated data was passed through 3 different imaging scripts. And then you would run the real data through these scripts, and that's what you would take. Yeah, it was a multi-stage process. Because imaging is, I mean, you can do interferometry if you don't do things right. You can turn this into an elephant if you want, right? If you can screw this badly up, right? And so that's why you first want to be sanity check, with just independent people and so forth.
Other questions or comments? One question for me: what can one realistically expect? How many black holes, different ones, could one see, say, in the next 20, 30 years?
Well, I mean, we'll do other black holes, but we will not see the shadow with this. From Earth, you can only do 2. From space, you can do like 5 more in the local neighborhood, like Centaurus A. And then you could do, I forgot to put this in, but then you could go to the deep universe, and so really big ones at high redshifts you could also do if you have enough sensitivity, and that could be actually quite a large number. And that's something we want to study in the next year, so how many you can expect. It depends on your configuration and how much money you have, right? So, in principle, you could build interferometers which can give you almost all black holes, right? Actually, thousands if you want.
Okay. If there are no further questions or comments, then let's thank Heino again.